Okay, first of all, what we're going to do is demonstrate a couple of synthesis reactions. All right, the first one is one you have seen, but I'm going to do one extra little thing on it. Cody, would you grab me the distilled water over there and bring it over? It's in a jug that says distilled water on the side. Hey, look, you found it. See that? I knew I had every faith in you. Alright, I'm going to pour a little water in here. Okay, and what I'm going to do is I'm going to add a couple of drops of this stuff, this phenolphthalein, which indicates if a basic solution or hydroxide ions show up, this will turn pink. Okay, right now you can see it's colorless. Okay. So the first reaction is going to take, you guys have seen this, and you know what not to do with this. When I light, could you let Ryan in? When I light the magnesium strip, you know that it's going to combust, and what product is formed from this? Magnesium what? Okay, remember guys, we did lab on this stuff. Okay. All right. Yeah, magnesium oxide.
Oh, the sun.
And it's very bright. It's not. Yeah, it's as bright as 1,000 suns. Just kidding. It's bright, so you don't want to stare at it, right? Okay. So but this time what I'm going to do is once I make the magnesium oxide with this, which is synthesis reaction number 1. I'm going to take the magnesium oxide, put it in water, and as you can see on your sheet, that'll give us synthesis reaction number 2, which produces hydroxide ions, which should turn the water some pinkish color. Alright, so we're going to get 2 for the price of 1. Okay, so here we go. Oh, so bright. Stick. My eyes. Okay, alright. Going over here. Don't stare. Alright, now there's the product, right? Magnesium oxide. Drop it in. Okay. Now, the reaction's kind of slow here, but the sharper eyed amongst us will notice that there's pink coloration on that oxide product right now. Okay? I better stand back in here. Okay? Can you see some pinkish stuff?
Yeah.
Alright. Well, we'll let it set, and it will make it more pink as time goes by. Alright, so that's good. That's a good one. Alright, so those are a couple synthesis reactions. You'll notice there's some little hints down here, and what you're supposed to do with those hints is write a balanced equation. So we'll see what happens with that. Okay, next is, right. Okay. Alright, I have in this container, this very old container, some potassium chlorate, and potassium chlorate is a white powder, as you can see. It looks sort of like sugar, so I can guarantee it wouldn't taste a bit like sugar. And it contains a lot of oxygen. Alrighty? So what we can do is dry that oxygen off and leave behind the chloride of potassium, which is called potassium chloride. But what's interesting is the oxygen. That's what we're after. Now, you guys know that oxygen is necessary for a person to survive. But what's the percentage of oxygen in the air? Not high. It's around 20. That's correct, yeah. But don't say 10. We'd be in trouble. And 25 is bad, too. 20 is good. We've learned to live to 20. Okay, so what would happen if you were in 100% oxygen?
You die. Why would you die?
Well, what? Yes. All right. Why would you die? Would you die instantly?
No.
Okay.
Maybe. Yes. I don't know the answer.
Well, you seem to know that we would die.
That's what Tyson said.
Oh, Tyson, yeah. Okay, well, yeah, I mean, first of all, in that kind of percentage of oxygen, our bodies would be flammable. So anybody got near you with a flame, you'd literally light on fire. And we couldn't put you out because everything around us would be flammable. In fact, in 100% oxygen, stuff that you don't normally think of that burns, like Peeps and Skittles and jelly beans and such, burn like rocket fuel. So what we'll do is I'll demonstrate that to you. I'll have to produce a pure oxygen environment, though. Okay, now some of you might have noticed we put a black powder in there. That's a catalyst. That'll speed up the rate of decomposition, right? You guys probably have heard of catalysts.
I heard of them.
Yeah. And then you knew that they speed up reactions, right? Yep. Almost everybody knows that. I have to do this in the hood because well, this one can cause some trouble if it's not. Sometimes things shoot out.
You're right.
Now, I'll take a little chunk of Peep.
Adorable.
Yeah, I was ripping ear off. That gave me some satisfaction. I'm going to drop that into the pure oxygen environment and see what happens. But we have to test for it first. Now, here's how I test it. See this thing?
Yeah.
It's called a wooden splint. Okay, no great surprise there, I suppose. All right, what I do to test for oxygen is I'll light this splint, blow it out, so it's still smoldering, and I'll put it near the mouth of that test tube. And if there's oxygen coming out, guess what happens to the splint?
It'll light up again.
It relights, right? Poof. And this is a test you guys will do in our lab this week or next, depending on how far we get. All right, now what you'll notice, can you all see this stuff? It'll start to melt first, and then you'll see some bubbling. Then I'll go in with the burning splint and see. It should go a little faster because of the catalyst in there, but it does take a minute or so.
Will the oxygen manually stay in there since it's denser than the surrounding?
It will escape because the heat will drive it out because it's hotter in there. So the gases will expand from the heat and will come out. But it is a little more dense than air. That's a good call, actually. Good thinking. All right, so some of us might notice some bubbling going on. Okay, and actually, I think maybe I'll pull that heat back just a little. Let's see if we got any oxygen in the print.
Whoa!
Anything? If you hear it, you might actually hear it pop. See, I think there's some oxygen being given off, don't you think?
Yeah, I think so.
Okay. Remember. It's relighting. Let's give it a little more of a boost there. and I'll take the heat away again and drop this sugar in. All right. Now sugar, you know, is flammable. Especially in a 100% oxygen environment. There we have it. And you can see it burns up quite rapidly. Yeah, actually the purple, well, the coloration of the flame purple comes from the potassium. So we'll show you. I'll throw a Skittle in there. It'll basically the same fate will be seen. Here comes a Skittle.
Oh, poor Pete. He's still burning.
Butterfingers.
We should put a Butterfinger in there.
Yeah, Butterfingers would work too, for that matter. Always somebody ready to boo. They're so unhappy.
Not enough fire.
Can we shoot the Skittle? Is that possible? Yeah, I want to see shoot that.
Well, occasionally that does happen. In fact, one time I did have it happen. It shot out, landed on some papers of mine, started them on fire. That was one of those memorable moments in chem teaching history that I'd like not to repeat.